Hi, today we're going to learn about the fundamental theorem of calculus. We learned that a definite integral, which is one of the integrals with little numbers on it, which represent an interval of x's over which we're finding an area, we learned about that being representative of a net area in 5.4. But at that time, we couldn't evaluate them on our own. We had some problems where we were interpreting things as net area based on information already given to us, but only now will we be able to evaluate a definite integral on our own. So it turns out that our first step of all of these problems is going to be the same as it was back in our very first section when we did indefinite integrals or antiderivatives. We are going to need to first find the antiderivative using those only three rules that we know from back in the beginning of this unit. So what we're going to see is if I wanted the area between an x value of a and an x value of b and the function and the x-axis, one way to think about that is if I found the area all the way from 0 to b and then I subtracted off the area I didn't want from 0 to a, then what I would be left with is just the area from a to b. And those are x's that I'm referring to when we talk about our interval. So we need to evaluate that antiderivative, and we're going to plug b into it and then subtract off that area we don't want by plugging a into it. So something you'll notice here, you will not need to write plus c's. They're showing you one time, and I might show you one more time, but then you shouldn't be doing it after that. If you did include the plus c's, which are just arbitrary constants, then when we do the subtraction, they're just going to cancel anyway. So what we'll find is with these definite integrals that we do not even bother writing plus c because it would cancel anyway. So down here at the bottom of your notes, you'll see what our strategy is going to be to solve these on our own. And that is that we're going to begin by just finding the regular antiderivative using the only three rules we know from the beginning of the unit. And then instead of putting a plus c, we're going to continue on and we're going to plug b into the entire thing, which basically gives us the area all the way from 0 to b. And then we're going to plug a into the whole thing, which and subtract it, which will then take off the area we didn't want. So to see our first example, and this is going to be, again, the second and last time where you'll see plus c's just to make the point, we are used to doing an indefinite integral where you don't see any numbers on it, but that is really our starting point. I still need to do the reverse power rule, which is how I get 9x minus x cubed over 3, and we're used to getting a plus c. But what we just learned is that I need to plug in the upper limit of integration, which they gave me as positive 3, and then I need to plug in the lower limit of integration, which they gave me as negative 3, and I need to subtract them. So those c's would cancel anyway. So again, I don't really want to see that in your work. I'll show you in the next example what your work should look like. But just to prove to you why things look differently and what would happen anyway. So we end up getting 36 square units. We don't have to have a picture in order to do this problem. But I just wanted to show you and help you see that that is reasonable and that it does literally represent the area that is here between the function and the x-axis. So it is representing this area. 36 is 9 times 4. If you look here and we go 4 units from negative 2 to 2, and you go up 9, notice that 9 is the top of the parabola anyway. So what I've outlined there in red is a 9 by 4 rectangle that has 36 square units in it. And if you look at the picture, you can kind of see how the extra pieces here on the outside almost would fit in the missing pieces in the top. So again, this is not something that you'll have to do for me or that you need the picture to solve, but just to kind of prove to yourself that that definite integral really does represent area, that there are 36 square units covered by the highlighted area. So here is our summary of what we've learned. If you are evaluating a definite integral, which is one that's going to have numbers, the limits of integration. So a is going to be the lower x in the interval that you were given, and b the upper limit of integration, the upper endpoint of what you were given. You're going to begin by just finding the regular antiderivative, which they're representing by capital F here, because it depends on what kind of function it is as to exactly what that'll look like. And then you're going to plug in the upper limit of integration into the entire thing minus the lower limit of integration into the entire thing. Being careful with parentheses as needed, because we might have multiple terms there in the second one. So here's what your work should look like for a problem without extra things like plus c's that we don't really need. So very first step will be the same as pretty much every problem we've done in this unit. I need to find the antiderivative of x squared, which is x cubed over 3, minus sign. I need to find the antiderivative of 4x, which is 4x squared over 2. Now I can go ahead and simplify that to a 2 before I continue, but I'm not going to put a plus c. I'm also not going to have an integral sign anymore or a dx anymore, because I did what they said. I found the antiderivative, which is what that integral sign and dx indicate. But I'm not done yet, which is why we're going to have, sometimes you'll see this as a straight bar and sometimes you'll see it as a bracket. I tend to do a bracket because sometimes then we could actually use the other side of a bracket and use it both for this antiderivative notation and as an actual grouping symbol like we're used to. So either of those is fine. But this says I've done the antiderivative, but I'm not done yet. I need to do something with these little numbers, so notice they stay at the same height as they were before. They're just here at the back now. So I'm going to plug negative 2 into the entire antiderivative that I found, x cubed over 3 minus, we've simplified it to 2x squared, minus parentheses. So I don't have to have the first set of parentheses that I just put in there, but it is kind of a nice habit to get into, and then it looks more uniform. But I absolutely must have the 2 parentheses that I just starred. And that's because I'm subtracting what happens when I plug negative 4 into the whole thing. And we have 2 terms, so that negative is going to affect things, and the parentheses is essential. So at this point, how much simplifying you do beforehand and how much you just type straight in is totally up to you. I will say doing at least a little bit by hand can prevent having so many typing errors just by having less to type. But at some point, you're going to type all this in, and the answer represents the area from an x of negative 4 to an x of negative 2 between the function x squared minus 4x and the axis, or the net area if sums above and sums below. So you could argue we technically need to put a unit squared here because that's what it is. That is not something that you will typically have to do. So let's look at another example. And what you'll see is these are all going to start the same as if this was from our very first section of this unit. What is the antiderivative of e to the x? It's e to the x. It may not look like I did anything, but I did because it's the coolest antiderivative ever. And the integral sign and dx are gone because I did what they said, but I'm not completely done, so this 2 and 0 indicate what I need to do next, which is to plug the 2 into the entire thing minus plug the 0 into the entire thing. So you might notice I didn't have extra parentheses there. That is because there's only one term, so I'm not really at risk of any issues from this negative sign. So e squared I can just leave as exact, and then e to the 0 is 1. And that's all there really is to it. So it's this step at the end of plugging in the upper and lower limits of integration, but the beginning is the same. So here's one more. Notice that I need a combination of my rules. The antiderivative of x, I need the reverse power rule. Add 1 to the power, divide by the new power. But I do not suggest rewriting 1 over x where we had a negative 1 power because then you might be tempted to try to do the reverse power rule. And it is its own rule, right? There is a function who has a derivative of 1 over x, and that is ln of x, where we use absolute value bars to be safe. So I've now done the antiderivative, but I'm not done because I haven't plugged in the e and the 1. I then plug the e into the whole thing. Again, this set of parentheses is not actually necessary, but it might be helpful just to be in the habit. But this set of parentheses absolutely is necessary, and hence why I didn't forget them. And plug 1 into the whole thing. And in general, unless you're told to round to some decimal, exact numbers are better. So that can just stay as e squared over 2. Ln of e is the nice number 1. And then we have a minus 1/2, and it would be a minus, but ln of 1 is just 0. So we end up with e squared over 2 plus 1/2. So here you see the limit definition, and we don't get into all of that, but I put it here to remind you that just as a derivative was formally defined by a limit, and so a lot of our properties came from limit laws, antiderivative, this definite integral, is also defined by a limit, and that is why we also have very similar rules to the limit laws if you look back at the properties from the last section. So the remaining notes are just kind of some word problems with this. If they give us a derivative function and ask us to get the original function, then we are integrating it. And when they give us these numbers or parameters, then that's our limits of integration. If you only see one number, then there really have to be two. So what does it mean? If you sell the first 60 seats, that's from 0 to 60. So that's going to be our limits of integration there. So what we need to do is find the antiderivative of the given function. I did need to rewrite square root of x is x to the 1/2. And then once I have the antiderivative, which here is just both reverse power rule, and let's see, add 1 to the power and divide by the new power. So we should have a 3/2 here in that location. So we can fix that. The number might end up being correct. But so I should have x to the 3/2 over 3/2 here in this highlighting area. Or I could replace that with a 2 and a 3 that I can flip and multiply. So sorry about the highlighter. And then reverse power rule here. And then I just plug the 60 into the whole thing and the 0 into the whole thing. Now, the fact that we end up with a negative number, even if it's slightly off from that typo, means that we have a loss because it's a real world problem. Also, notice our units were in hundreds of dollars. And so if you're actually interpreting it for real, if it is negative 50.16, then it would be 50,016 if my little typo gets it a little bit off. It's still the same principle. So it means that they would have a loss of 5,016. Now that should make sense to you because sometimes your flights are canceled. And so if they say if they only fill 60 seats, they're still going to be at a loss of $5,000. They still haven't covered the cost of the fuel and the flight attendants and the snacks they give you and the pilot. And so they're going to put you on another plane that's going to be more full so they can actually make a profit. So if you notice, that I've got this area below the axis, and then I start getting area above the axis, but it is less. So until there is more area above the axis than below, we're not going to break even or start making a profit. So that's kind of an interesting one because you may have actually suffered the consequences of the fact that airlines really do use something like this. As another example, again, we're given a derivative, we're asked something about an original cost function, and we're given two numbers. Now, sometimes you're just straight up given those two numbers here. Those two numbers we have to be a little careful with. It says 14 more after 50 feet have already been done. So that means we're going from 50 to 50 plus 14, which is 64. So we're going to do the reverse power rule, add 1 to the power, divide by the new power, or multiply by its reciprocal. And then we need to plug 64 into the whole thing minus parentheses 50 into the whole thing. And at some point, you're going to need to type it into your calculator. So we get that to do those extra 14 feet, it would be the 2913 extra. All right, let's look at one more and maybe we'll do a separate video for average value. So this is a good example because it really kind of pulls things from the entire course together. We do have that relationship of revenue, profit is revenue minus cost. If you add derivatives to everything, then that relationship is going to hold. So they give us information about revenue derivative and cost derivative, and we're asked about the first 10 days, which would be 0 to 10. So that's what we're integrating. We need to integrate r prime minus c prime to get back to regular p, and we're going from 0 to 10. So a really common mistake I see with this is people realizing they need to subtract, realizing they need to find the antiderivative, but then just plugging 10 in. And I understand that if you do enough of these problems, you feel like every time you plug in a 0, you just get 0, and you might be used to discounting it. But remember, e to the 0 is not 0. So we're actually going to get something substantial from that term. All right, so revenue minus cost. It is minus parentheses cost because there are two terms and we need to distribute that negative sign, which will affect things. Then, as we're practicing now with this fundamental theorem of calculus, these definite integrals, what I often find is students get so hung up on the plugging in the 10 minus plugging in the 0 that they never integrate. And that is a problem, right? That's what this entire unit is about. So we absolutely must first do what the integral sign says, which is to do antiderivatives. With e, it's itself, so 100e to the t, minus the antiderivative of 100 is 100t, plus here I need to add 1 to the power and divide by the new power. Well, I'd have 0.2t squared over 2. But 0.2 over 2 is just 0.1. Then we plug in our 10 and our 0. So we're going to plug 10 into that entire thing minus parentheses 0 into the entire thing. And what I was warning you about is here, e to the 0 is 1. So this is actually going to be 100. 100 times 1. Yeah, the other terms go away, but you would be off by 100 or 200 if you forgot about that. So at some point you can start typing in your calculator. And we get, so this was my company, remember, that in 10 days I make $2,201,556.58 as my total profit for the first 10 days. All right, so we are going to cover average value, but I don't want the videos to get too long, so we'll visit that in the next video.